Okay, so here we are. Let's dive into the thermal analysis workflow. So we remember that we're using this drop down and we choose the thermal analysis and we get this dialog here. Um, Before we get into it, let's talk about why do I have this form right here. I've got each floor has 5 different zones. There's a specific reason for this, and that is that so the everything that we're going to see in these models is important to understand and remember that the only value to this is if it's coming from a standard or that we're changing a standard in a way that we understand. And that's because, so what are these standards? So for example, there's an organization called the ASTM, American Society for Testing Materials. There's another one, ASHRAE, um, the American Society for Heating, Refrigeration, Air Conditioning Engineers, which I think they've changed their name now to mean to something else. Those two organizations often work together. I think it's the whole thing is kind of confusing, but it's also incredible. So because what's going on is like so ASTM, for example, they create the standards for pretty much anything. If you're making brass, um, there's a standard that tells you the properties of that material have to be if you want to call it brass 360 as opposed to brass 470 or as opposed to some copper alloy or whatever. Um, and if, of course, if you didn't do that, how would somebody be able to buy brass to make a plumbing fixture out of if they had no idea what the material properties of it were, right? So they create these standards that then people follow so that you're comparing apples to apples in the world of getting things done. And that all works. Those are engineers and other people who get together. They're on these committees. They come up with these standards. It's a long process, and there's thousands of them. So while we watch the world struggle to get along in the most basic ways, we've got like scientists, engineers, and other professionals that are just cooperating at an incredible level. So I find it really well. First of all, it's how anything gets done. So we're part of that, and we want to respect it. Or what? And a lot of times I hear architects complaining, like professional architects or academic architects, that we're losing our place in the world. One reason why is I think that a lot of people don't take us seriously because we aren't rigorous like this. We don't understand that it's important that whatever amazing spaces that we're imagining and wanting to create for whatever reasons we have, they've also got to be grounded in the real world. Anyway, so this is how we do it, is that we just are conscious. I'm not saying that this is an engineering class or that we're engineers, but we need to be somewhat technical. Um, and sorry, I'm going off on a little soapbox here, but it's important. If you talk to somebody who was an architect trained in Germany, they do this. Or even Canada. It's just some in the United States we tend to be in the art school architects, and which is great, but we sometimes lose that full perspective, and so that's important, especially when we're modeling, that we realize that we're a part of that. I just got a phone call. Anyway, Saturday morning, I'm just rambling, but those are gems that you should listen to. Point is that this is where I got that weird shape from, and there's a bunch of them. This is from the I didn't mention, so ASHRAE 90.1 is the standard that you'll often see quoted. It's everywhere. It's where a lot of the performance information comes from that we use in architecture, especially high performance architecture or contemporary architecture, which has to be high performance. Um, and so there's a bunch of predetermined building types in that standard, and I chose the medium office just for my little practice thing. You may want to at some point look at this and choose one, and then look it up and see what that means in terms of the requirements. For right now, you don't need to do that. You can just model whatever you want to, and it's better just to play around. So that's why I have this shape. So let's go over now just the workflow for thermal analysis. I think I'm not going to start with this because I've already got a million zones in here. I've done a bunch of runs. So let's just start with something simpler um, to learn the interface. So I have a very basic little volume here. I've got a ground surface, an opaque envelope, a window, and some shading. So if I all I have to do to start a thermal analysis in Climate Studio is to set some parameters for these different features. Um, so I guess let's just do that, and then I'll talk about it as I go. So we have to have our climate. That's important, obviously. But so let's say these are the I can create a zone. Oh, this is what I wanted to say. This is a I could have a separate. Let me right. I could have a separate volume that was my architectural model, and it could be in the same place as this. It could be more ornate. It could have other features. What I'm defining here in the thermal analysis, so what I'm saying is I don't have an architectural model right now. I'm just doing the thermal model, but they are not the same, and I don't have to create the same level of complexity in my thermal model that I would in my architectural design. What this is, I'm going to make this a zone. A zone is simply a volume of air that's bounded by some surfaces or some, assemblies that have physical properties that we define. So I'm just saying I want my building to have, or this zone is going to have this volume of air. Um, I can, these are the things I can identify in my thermal model. A zone or zones, windows, exterior windows, interior windows, shading, the ground, if I'm sitting on the ground, and what's called an adiabatic boundary. So I need to create boundaries around my model. I need to define what are the volumetric zones that are surrounded by something. Do they have windows, interior and exterior windows? Are they shaded? So I'm going to say this is my thermal zone. I'm going to click this button for zone, and then now this dialog shows up. What is this? This is a huge amount of information here. I'm going to start by, I'm just going to pick, one thing you'll notice too, there's no single family house in any of this. This is a huge list of stuff. You see, oh, look, there's 90.1. Let me, here's a different standard. Here's 90.1, tons of 90.1. That's from that standard I was just talking about. So um, these are all based on um, either standards that this this is some Swiss thing that they're into, SIA Merck Block 2024. So these are Climate Studios has various standards that you can access. So this is just a library they've created. Um, so let's just pick multifamily housing as a beginning point. And if I I'm going to say this is a multi, and we'll talk about what that means in a minute. Let's just run a quick model. Um, I can so I've got a zone. Um, I want actually let's just run that. I don't even know how big this is, so I can run a thermal model right now. It's running. Oh, by the way, there's a um, sorry, I just realized that this is I'd used this file before. This is a good moment to talk about this. So this is the result that I just of the model I just ran. And you can see we have an output like we saw in the introduction that we'll talk about later. What's the rest of it? What's all this red stuff? This is that I had used this file, I guess, for and run some other models. I didn't. I just made it, so I'm not made. No, I guess it was something basic here. These are all. This is so when you run a model, it is saved in the folder wherever your model is. And so this is looking for models that it doesn't know where they are, move them or delete them or something. I'm just going to delete those. Okay, so here's my the run I just made. All it is a zone though, so let's add some more stuff. I'm going to add the ground to it. And so what's the idea here? It's that, so think about it. This is a zone. I'm basically saying this volume of air. I want to have a different interior environment than an exterior environment, and I'm going to surround it. What's it surrounded by? That's what the model needs to know. Well, I'm going to say, well, I'm going to define this envelope. I'm going to tell you what's going on inside of it because that's going to change the internal heat gains. Um, but it's assumed then that so I've got this zone and there's nothing touching it, that's all just got air around it from this climate. But that's not true, right? It's sitting on the ground. So I'm going to select that and identify that as a ground boundary. And actually, this is left over from those other models. I'm going to delete that. It wouldn't matter. It would change it, but I'm just showing that this does start. Um, so I'm choosing this icon, which is the ground. And now I have this ground boundary. If I come to wireframe, it shows up as green. So now this is my model. What shows up in this wireframe display is shown here in the previews. So right now I'm previewing everything. So you can turn those on and off. Like if I didn't want to see the ground, I think that would be, or if I don't want to see the facades, right? So I got rid of it there. Um, let's go and turn them all back on though. Okay. So, oh, and by the way, I think it's because I ran this before. This looks like this is a window already there. Let's see if it even put it in. Did it? I don't think it did. Oh yeah. So that's actually already, I'm going to delete that window. I'm going to delete both these windows. And let's sure that, oh, there's a back window, right? So I'm actually going to go delete that model. This just shows you kind of I'm just playing around here, but how quickly you can change things. So I didn't realize that there were already windows in there. So I'm going to go back to the beginning. I'm just going to turn off. Oh, and did I have shading? No, I didn't have shading. Why was it saying I did? Oh, that's just the physical, the modeled surface. Okay. So that's a good point. What you're seeing in your model is not necessarily, that has nothing to do with what's in what you're seeing on your screen has nothing to do with what's in the model. You have to be conscious that this is just display, so you may not be displaying the model, right? Okay, I'm going to, and that's why we would go to shading to see what's on the model. So right now we have a zone. Let's just delete that again so we can start from scratch. Right now there's nothing in the model. I'm going to select this zone, make it a zone, and I'm going to do the multifamily housing again. So I've got that. I shouldn't have, I do have a boundary. I'm going to get rid of that. Because I want to run it without it and see what happens. So I'm running, by the way, let me just see if I can show you quickly. When I run this, a DOS window opens up. I have two screens, so that's why you don't usually see it. Okay, so here's our initial model. And it's really important that you name these. I'm not going to do it right now. Or maybe I'll just do it because I'll say zone. Um, let me show you what I did for. So this is the spreadsheet that I made for the runs that I've done so far. I kept detailed track of what all my settings were. It's not a bad thing to do. If you're playing around, you may not want to spend the time on it. You can also download your results down here as like a report. We'll have all the data in it, and we'll have all the settings. It's just there's a lot in there, and so it's not really very easy to follow. And the point is, if I start running these analyses, and I'm having fun. I'm like, yeah, this is really interesting. And then I've just got a bunch of names up here. They're energy one, energy two, energy three. I very quickly it's useless because I don't know what I've changed. And the other thing is when you're modeling, it's a good idea to try to change one thing at a time because then you can really understand what the effect of that change was. So let's do that right now. I've got a single zone I ran. I'm at 49 site EUI. energy use intensity. Let's look at that for a second. So, and we're in IP. Okay. By the way, this is the other number I think is wrong. So just ignore, not that you're thinking about it, but just realize that I think that this operational carbon in IP is wrong. If I go to SI units, if you mess with this, well, I won't even talk about it. Just realize that that's probably wrong. um, okay, let's just look at a couple things real quick, just to show, because I think it's interesting at this point. Um, the energy use intensity, this is per square foot per year. Um, you can also do the energy use not per square foot, so it's going to be the total for the building. So you might want to do that just to see. This gives you a rundown on how much you're using it per month total. But what this does is allows us to compare apples to apples because it's per square foot. So if we were looking at a skin load versus a internal load building, this would be different for reasons that we could understand if we, but we might want to see it as per square foot, but then we could see, the difference between a really small building and a large building, what per square foot they were using based on their different settings. Um, this baseline EUI, this is from a Department of Energy, or this, let's just say standard 90.1. Those prototypes, they went out and did a big survey, and they came up with an average for buildings of this type. So the multifamily that we chose. So this is what we're shooting for as a baseline. This makes right now our building without any windows or anything, and it is the average. Kind of interesting that it's exactly the average. Okay, anyway, let's go back and add the slab, the ground. So I'm going to select, I'm going to turn it on, leave this on. Sorry, it says I can't see it because, there we go. And I'm going to add it as the ground, and there it is, we can see it. I'm going to run my analysis and see if that changed anything. And it did. So we went from 49 site EUI to 42. And I'm just going to put ground here so we have some context. And this is really simple point, well made though. This looks exactly the same. If we're looking at the actual building, there's no difference between these two models. By the way, right, as I click through these models, it doesn't change anything in the view. That's why you really have to keep track of these models as you make them. There's no way to now go view this that I know of, to go view this actual model. I can view what the one I just did, but I can't view the last one. Now, if you're doing a daylighting study, that's not the case. It keeps track of the visuals. So this is what we're seeing is just the last thing we ran. But anyway, it looks exactly the same, the actual model, but it's very different. So that's why this is a different type of design where it's not all visual based. So you have to be you have to be disciplined about it. All right, so now let's just keep going. I have added a zone, the ground, and now let's add a window or some windows. So I'm gonna turn on my fenestration layer. I'm gonna add that surface and that surface, or I could have just selected the whole layer. I want to add windows, and now I'm just these are the settings right now. It's just set on default glazing. We'll just leave it at that for now because we can edit it however we want to. And you see what happens is that now it brings that window into the correct zone or the correct face. So this is, let's see, that's the north window and this is the south window. So this brings up another point. That's why if you look at this model, another advantage of having these different zones is that I can name them in some detail. So I've got, the west, the east on the third floor. So two west, two east, two north, etc. So that if I'm looking at the window that's in this zone that's inside this facade, I don't have any windows in this one. Oh, that's right, I took them out of there. So let me go to the south. Um, now there's actually a window on this facade, and so I know where it is, and so by identifying it. And this other model with a zone name, if I don't have a way of identifying this space itself because for some reason you can't edit these names here, which I find really strange. But anyway, so I know this can get really complicated quickly talking about it. So you can scroll through these things. I'm just trying to point out as many of the details as I can, so you have some place to start. Okay, so let's run that. So now we've got um, a zone, ground, and windows, and we should get a different result. As to be expected, we have a much higher. Oh, but by the way, so what was the deal with the zone, the ground zone lowered our EUI, and we have now have no cooling load. There were no windows. Why would that be true? Well, if we have air, maybe this is highlighted. Another way you can do that is if you're in results and you say show no results, it should turn off. Um, anyway, so in the ground, it's lower because this is, if we're not exposed to air and we're touching the ground, we could lose heat through it at a time we don't want to, but in general, it's like, much more stable temperature at the ground level. I mean, the ground itself, even though it's not, 68 degrees that we would want it to be, it's to say it's 55 degrees pretty much year round maybe, or there's some fluctuation there. But that's going to be less heat loss than the air around the building, right? So that's why that changed from 49 to 42. And what's the process there? You want to, as you're doing these models, see if you understand the change. If you don't, you need to either go understand it, or then you'll realize, oh, I did something wrong, which is so easy to do. You can thank you like I did at the beginning. I didn't realize I had windows in there, right? Um, so now this is with Windows, and our EOI went way up. Why is that? Well, because Windows have typically a much lower um, U value, or a much higher U value, much lower R value than um, solid opaque surfaces. So if we add a window, we're gonna go down in EUI. Um, By the way, if you don't know what R value is, what U value is, any of the terms that I bring up, then you just need to ask me because I need to know that. I really, honestly, you should know that, in my opinion, at this point in your careers. And I know that Sabrina and Fatima are talking about R values and the things I've seen from them. But don't hesitate to tell me that I'm getting into too much detail, or that there's, that I need to spend time in the materials for the class identifying some of these things. And I will, but I mean, I may not do it enough. Okay, so now we have, um, let's add one more thing. We've got our building zone, our volume, we've got a window, we've got ground, we got windows, grounds. Let's add some shading. So let's add this guy to shading. And if you don't do that, if you see, you're going to have all this shading in your project, but if you don't add it to shading in the model, it's obviously not going to shade. Um, and wait, I didn't do it. Shading's here. And there it is. So we have shading. Let's run the analysis. And now we see that actually increased our EUI, which means that we were getting some solar gain that we wanted. Probably, I could go in and analyze this. Now, this is going to be already pretty long, this little introduction, so I won't do it. But the point is here now we're going to add shade. It'd be a good thing for you to do this on your own and ask yourself why, based on looking at comparing. We definitely have more heating load, looks like here. By the way, also notice that sometimes as I change these, especially in the square foot, um, This is a really small building, I think. I don't even remember how big I made it. So it's may not do it, but these scales change in range. So sometimes it may look like nothing changed, but you got a drastic change because the y-axis value changed. Um, oh yeah, these are really small. So this is a small building. Um, but let's see. So our heating loads went up a little bit. Our cooling load went down because we shaded. This is the cooling load here. So this is going to go down from the window to the shade, right? So that makes sense. But then our heating loads went up, and I think that's because we were getting some desired solar gain through that window. And this, so let's see if we, actually, I'm just going to shrink it down a little bit. So I think that just will adjust it without having to do anything else. Let's see, let's do it. We'll run it. Let's see if that changed. Because the idea would be that, and I could actually now let's do that too. Let's see. Yeah, so we lowered our SUI, our EUI here because I made this shade smaller, and that's because I'm letting some sun in the winter, so my heating load should be going down a little bit. Yeah, so see the heating load here goes down a little bit because I'm now letting sun in with that overhang into this glass. I'm losing a lot of heat through the glass, but I'm also gaining some. And so the balance is in the favor of having that overhang. But is it? Let's see. It's almost the same. So now we're kind of back to where we were with the window itself. We're a little bit better in our carbon here, and this is a big number. So like we're probably at 54.2 here and 54.5 here, or something like that. And then I could go back and turn on my sun and ask myself more like, well, okay, why did this happen? Is that true that, I'm shading at a certain time of year with this overhang, and I could go back and forth between this visual interface and the thermal model, which is pretty cool. All right. Oh, wait, let me go back to the sun and that's another reason why you might want to have these open so you don't have to keep working back and forth. I'm going to turn those off. Go back to the thermal model. Okay. One more thing to say about that is this is where um, the site would start making sense. Or I mean, there's other things at this point that already make sense for site too. But if I had, this, um, and I made this object a building, and I wanted then to make it a shading item, which I just did. See, so that's now a shading item. It's also gonna, let's just see if let's run it. Oh, it's fine. It just says the backside. I mean, I'm not gonna mess with that. I could change it to where you had it. It may not do anything because that's pretty far away from the building. Let's just see if that shading did anything. Um, it definitely was, compared to that shade, it's causing more shade, and we're back to the same problem we had before with the losing our heat gain through that window. And again, if that doesn't make sense, you're like, what is he talking about with the heat gain? And just you got to ask me. What I'm trying to do is just get you guys started on the thermal model in this interface. All right, so let's call this. All right, so that's our first little foray into modeling. Let's get deeper into it. Uh, So let's look at this more complex model. I'm going to just get to know these little tools over here. This collapses, or that expands, this collapses. Um, so let's, I'm clicking on a zone and now I'm going to edit it. So this is going to allow me to look at the settings. Um, I'm going to go to, actually I'll do that. So I'm going to the settings. This is the power of this is using templates. So I'm going to go right to that. I'm going to select this little, so I clicked on a zone. I want to edit the settings for the zone. If I go to this little icon here for settings, I can apply a template, and now I come to that template uh, dialog that I showed you before. Let's, I created a bunch of templates, and these are the runs I did in this model. So let's just open this one. You can see that I can edit them because I created them. So I'm going to edit this, and then I'm going to show you how to make them, and why you might want to do this. I can also share these with you that I made. I made them for a specific reason. But let's just use this. I just picked one randomly. This is what I call 1960 baseline. This is me trying to approximate a building like the Guggenheim. Just using the concept of the 60s, like what they would have been thinking about, and the technology they had. So the first thing when you create a zone, or your template zones, they they utilize those, the ones you create are at the bottom. They utilize those building typologies that we talked about. So like medium-sized building, or medium office or whatever. So you have to identify that and in the name. But by the way, these are just to help you catalog. These don't change anything about the actual performance. These first two, oh, I'm sorry, wait. We have 4 tabs here: loads, conditioning, envelope, and settings. We're going to go through these individually. These all are related to the thermal performance of your building. So in the loads tab, these first 2 settings are just for your purpose. They show up over here in uh, the description of in your model um, layout, I guess you'd call it, or your chart. But they don't change the performance of the building, just so you know that. So the different tabs: people. We said that people create heat, and there's actually you can look it up in the 90.1 standard, how much heat people produce, the average person, and based on their activity type. So um, the people density is defined by occupancy. So an office is going to be different than a house. The metabolic rate is based on what, if it's in a warehouse, it's going to be fewer people, but a lot more activity. So that is, again, a standard. I think 1 is somebody at rest. Um, then you can schedule how often the people are in the building. Airspeed would be how much just the typical air movement in the building is going to be. Remember that human comfort is a function of dry bulb temperature, relative humidity, mean radiant temperature, and airspeed. So that's why that's there. So anyway, people, and that's going to be based on your occupancy. Equipment. This is just a setting for how much heat the equipment's going to put out. Okay, so like based on, do you have a boiler? Do you have a heat pump? There's different. So it's a general setting. These are also set in standards. This one I put really high because I'm thinking at that time it would have been just things wouldn't have been as efficient, or they would have been thinking about this. Lighting power density. So basically, we're saying this is the amount of energy that the heat that the equipment in your building is going to put into the building. Lighting, obviously, incandescence. If you don't know about this stuff, we should learn that in environmental systems too. But the idea is that incandescent light bulbs are uh, basically little heaters that they let off waste light. Basically, this is just a little bit of light that they let off, and most of it's heat. And that we've gotten LEDs now, which are pretty much pervasive, are put off very little heat uh, compared to incandescent. So that's something that would have been different between 1960 and now. You can also schedule when the equipment's on. You can schedule when the lighting is on. And if you click on these, you'll see that there's a ton of schedules that you could select, and and this is a graphic of when the lights are going to be on. Um, a luminance target. This is going to be how many foot candles at whatever 4 feet or whatever you've set that at. That's again a standard. Um, that's another thing that's changed a lot over time. Hot water, your inlet temperature, so like what's coming from the city, the temperature of the water coming from the city, what your set point is, if your water heater is always on, flow rate per person. We don't need to get into detail on that. I think you can just understand that there's this would all be part of the loads from what's in the building, so that's why it's on this tab. And you can start to see the power though of these templates. I'm not saying that that every student's going to need to study these and I hope they would understand them, but um, these will be preset for most things. So when we pick a medium office, it's going to have a specific person, number of people per square foot. It's going to have a metabolic rate that will be preset by some template that we choose. Okay, so then we go to conditioning. This is the mechanical system of the building. We have set points, so the temperature that we start heating at, the maximum temperature that the equipment's going to put out. So, well, that's sort of self-explanatory. Some other stuff that maybe you don't need to worry about right now, that the maximum heating capacity, maximum heat flow, but that's getting into some pretty fine detailing. We're not going to worry about it right this minute. COP, though, is important, and if you don't know what that is, that's coefficient of performance. Simply the idea that different equipment, different systems are more or less efficient in how they deliver heat. A COP of 1 would be, for example, electric resistance heating. You put in 1 unit of heat or of energy, you get 1 unit out because it's pretty pure. Uh, like a gas system would be less than this, maybe 85, or it could be 90, a little bit more. So it'd be 0.8 or 0.9 because you're wasting energy by burning the fuel. You don't get all of the energy out of it. Um, but heat pumps, because they don't make heat, they move heat from one place to another. They can have COPs well above 1, 3, 4, 5. So that's something that we're going to change, and that's heat pumps are not something that they had in the 60s. So, or they had refrigerators, but they didn't have the kind of heat pumps we have. So this is a place that we can get a lot of gain or reduction in our large building energy usage. Humidity control, just whether or not you want to control humidity in your building. Um, I would think you would. I can't imagine any time that we wouldn't want to keep humidity at least below 80, because you get above that, you're going to start having mold everywhere. But anyway, that's part of the conditioning system. Mechanical ventilation. This is setting up how much fresh air. This is also done by these are standards. If you have a really efficient building, but you're not bringing fresh air in, people die. That's kind of counterproductive. I mean, that doesn't happen ever, but or they get sick. Legionnaire's disease. I don't know if you heard about that, but there have been problems with this. But it's also a huge part of the energy efficiency, because if you start bringing outside air in, and it's winter, for example, you've spent a lot of money and effort creating a temperature inside, and then you're just bringing in the outside. Um, so that's why you would use heat recovery, which is pretty standard now, but did not exist in 1960, so that you have a way of pulling some of the heat or cool out of the air that you're exhausting and putting it into the air that you're bringing in. And these are either sensible or latent. Let me turn this on so I'll talk about that at some point. If you don't know what that is, don't worry about it right now. And they have different efficiency levels. Again, these you could just run a model without knowing anything about these, because you would use a preset. But I'm letting you know it's here. Now, here's a natural ventilation tab. That there's a whole cool little workflow that we can go over at some point, that we can, at a very basic level, start modeling natural ventilation, as opposed to just saying, oh, I've got wind coming in with my windrows and I'm going to open my windows. This is actually um, uh, The default here would be just to do it with stack-driven flow, meaning you have your windows open, but there's no wind, and how much there's still going to be air moving, um, and how much natural ventilation you get from that. Anyway, I think just if you think about it for a second, I know I'm going through all this stuff really quickly, but that's really powerful. The difference between that step and the windrows shows you kind of why this is good to be doing, I think. So the point of the second tab, it's just defining our mechanical system in some detail. This is not in any way the detail that a mechanical engineer would need. Um, Climate Studio is really a sort of a schematic level design tool. For our purposes, it's crazy complicated and complex enough. But I'm just telling you, this is still very simple, and I'm not claiming that we should be engineers here. I'm saying that we need to be intelligent and give engineers things to work with that they don't think they need to change everything that we did, like tell us we need more space or that we can't have this window. Um, okay, then the envelope. This is defining um, the opaque portion of the envelope. So, is it concrete? Is it framed? Does it have insulation or not? Let's look at these for a second. So here's the roof of this. Um, this is just all concrete because this is a 1960s. This is the Guggenheim. But let's just look at uh, what metrics we have here. We have U value. Hopefully you know what these are, but if you don't, we can talk about it. U value is usually an assembly number. This is really a place that you need to, like if you look at my that little conversion factor thing I was showing you, I have a thing in here for converting between IP and metric U and R values because if it's the same letter U, right? But if you're using USI, it's very different than UIP, and you need to make sure that you know what values these are. So that's why you would know if you see BTUs, that's where in IP. This would be kWh, kilowatt hours, if it was in a much more sensible um, metric system. A BTU is how much energy it takes to raise the temperature of water, a pound of water, 1 degree Fahrenheit. Why the hell that has anything to do with what we're talking about? I don't know, but it's just something that's how somebody who was experimenting in some lab and came up with something that then became the standard. Um, that's the problem with the IP system. It's very arbitrary. Anywho, R value is the reciprocal of U value. Thermal capacitance takes into consideration how much mass the whatever it is we're talking about has. If it has mass, it may not have resistance to heat flow, but it will hold heat, and that has advantages in terms of reducing the amount of heat moving through something. So I can talk about that in as much detail as somebody wants, but that's the basic idea. And then we have embodied energy, so carbon footprints for these materials. The point here is that we can, or a point is that we can edit these. And so I've, like, for example, made other envelopes here. It's really easy to do. It's something you can play around with. But the point is that we can create whatever envelope we want to, and we do it by having access to um, a bunch of materials. Let's see. So I'm editing one of these. I can go pick from a huge array of materials that are available. These are also a lot of them queued to standards, um, or I can make up my own. So there's a lot of power we have here. Point is though that we're setting the envelopes for all these different uh, parts of our envelope. So we have the roof, obviously here, and these have these nice little graphics to show you what. So the facade. This setting is for the exterior walls, partitions, slabs. The graphic tells you what it's referring to. Another huge additional internal mass, because mass has thermal properties that can be important. We're just going to ignore that for right now. Air infiltration is huge. If you think about it, um, whatever you do in terms of trying to control heat flow, if you have a bunch of leaks in your envelope, that's going to completely undercut it, right? So the more airtight you can make the building, the better, but it costs money to do that. Old buildings like the Guggenheim, concrete is really the volume of concrete is very airtight, so that's good. But then I'm sure they weren't considering it around the windows, and so it's probably a very leaky building. Um, so this is a big parameter that we need to know about. It's very in larger buildings, it has a huge effect. Um, and then this is defining how the ground is modeled thermally. This we're choosing ground temperature based on the climate data. They'll have some uh, they'll have data on how the temperature, what the temperature of the ground is at different times of the year. But there's other models we could pick, but of course we won't worry about that right now. So that's the envelope, and then settings is just all the carbon and cost metrics that we can change, and we're not going to worry about that right now. It's just it doesn't change the model. It changes how much carbon and how much money we're having to spend on energy. So we can change that at any point to based on, for example, local 97 has specific. Actually, let's look at that again. This kilograms per kBTU, another good example. Why is it kilograms? That's metric. Kilobtus is IP. So they've combined these two here. So that means you have to do a conversion. The stuff in the local 97 is in probably in 1,000 pounds per kilobtu, or it could be 1,000 pounds per kilowatt. So let's just not get into that right now exactly. I spent the entire day yesterday after we had our meeting, trying to once and for all get this worked out as to how it's going to correlate local law 97. That's what this thing was all about. So I'm just letting you know that this will be very clear at some point. Right now, we don't need to worry about it. Okay. So what have we accomplished here? We have talked about all of the settings very quickly that determine the uh, uh, the resistance to heat movement and, well, just the thermal um, uh, architecture of our building. And we can now quickly change these to run different models. And that's what I've done. Okay. So that's the thermal zone. Now we got to talk about windows. So I'm going to go into one of my zones. Oops, sorry. Open up my zones. I don't have any west windows. Let me show you where my windows are. At this point, I only have windows in the north and south. So that's why there's only windows in these zones. And that was part of the whole iteration I did that I'll talk about in a second. So let's edit a window to see what these properties are. Again, this is stuff that I know that this is like I told you, the two that I met with yesterday, Sabrina and Fatima, that there's, I don't know, I think I said 150 variables or 100. I mean, that might have been an exaggeration, but not too much. And it's all building science related. So if you don't have the background in this, it's going to be confusing. Just let me know. I'll go into as much detail of that on those topics in the class materials as we think we need to. But let's not use this. Let's go to a default glazing. Same thing with these. I can type in a name and this is searching in the database. So this is the default single pane glazing that's set in Climate Studio. Single pane glazing, I'm pretty sure everywhere now is illegal. If you're building a new building, it used to be like I was in the I was looking at the room I was in our building off of Columbus Circle, and it had single pane glass. Definitely the entire building, at the old Westbury campus at Hall is all single pane. But now often you'll use triple pane, or there's even more. Anyway, so what are our metrics here? U value, already talked about it. That's what I actually said. That is the heat transmittance So what is it? It's BTUs, so that's the amount of heat per square foot of surface per degree Fahrenheit per hour. Um, so that's the amount of heat moving through. The reciprocal of that is R value. And so if we were looking at an opaque, usually you use U value for assemblies, and a window is an assembly typically, so that's why we use U value for those. You don't see R value here because you never hear windows as um, measured in R value, but it's just the reciprocal. So when you're looking at the opaque, um, let's just even do that. Well, I think we did. It's just going to be reciprocal of this. Um, a U value of 1 is really bad because that would be an R value of 1. And a typical, even just a cheesy wood frame wall is going to have an R15 or something like that. So windows have a very low resistance to very high, very low resistance to heat flow. Solar heat gain, so that's one of the variables. Solar heat gain coefficient is the percentage of solar heat that's going through the glass. So this is letting in 90% of the heat that's hitting it, which is great if you're trying to collect heat, if bad if you don't. And the visibility is the same. It's a ratio. So this is letting in 90% of the visible light, right? So there's different, in the electromagnetic spectrum, different wavelengths are for heat and for visible light. So those are different numbers. This, in high performance glazing, I'll show you some in a second. We can do amazing things by changing these numbers. Um, you have to be careful. A lot of the glazing has very low visibility though, so you just be conscious of that. Anyway, so we can choose whatever glazing we want. So let's look at a different, actually I'm gonna do it this way. I'm going to organize this in terms of U value. So the most energy efficient window in this database has a U value of 0.1, which is 10 times better than the one we were looking at before, right? So that's pretty good. But this has a solar heat gain coefficient of only 0.2, so letting very little heat through, which maybe that's what you want because you're in the sun and you don't have any overhangs. But there are times when you would want to get more solar heat gain than that. And so there are other, like here's one that's 0.138, so a lot more, it's letting a lot more heat out than the zero point 0.1, but it has a solar heat gain coefficient of 0.76 and a really good, for this kind of glass, visual 0.61. You'll see some of these, yeah, here's like the visibility here. Well, here's one 0.06. So that's like 6%. That's terrible. Um, I mean, less than, no, that's less than 1%. No, yeah, that's 6%. Sorry. But some only have 25%. So you have to be thinking when you're selecting these things what effect it's going to have on the space. Um, and that'll also come back later in the daylighting analyses. We can also turn on and off a shading system. These are motorized shades that are triggered by some variable. They can be scheduled. We'll talk about that later. Um, So our envelope, we can define the opaque zone and the window zone performance, right? Um, so now let me just go through these different runs I did and show you what I changed and why I changed it to give you some kind of feel for how this all works. There's a lot to talk about in terms of these different metrics, but I think that this is almost an hour already. I think this will be enough to get you started, and we can talk about it. And I can add whatever else. You guys can let me know if I'm just talking too fast and you don't understand any of it or whatever. Just give me some input and we can continue from there. Um, but I think it's good to um, look at these results and talk about them. So what I did first is I set what I thought was what I just made up as a typical 1960s commercial building. I made this out of concrete, but it could have been something else, obviously. So let's go look at that. And the way I'm going to do that is oh, actually, I didn't show you this. This is where the library is right here. I mean, I can access it by coming into a zone, or I can go to the library here. So I'm going to open up the library and show you what I changed for these different. Um, these different templates. By the way, so if I want to create a new template, I can pick something that's similar to what I wanted, but I don't have to. But let's say I select this. If I come down here and I say add, we just say test. I add it, and that shows up here at the bottom, and now I can edit it, right? So it will have whatever I use as the template. It will, of course, have their settings, but I can now go change those. I can also export libraries and import them. So like here's my user library. Um, but what happens, and this something glitched on this at one point, so I'm a little bit, but it's been now stable for 4 or 5 days. Um, Once you add one of these, this library is resident in Rhino, or I'm sorry, in Climate Studio. And once you add something to it, it's just there. So it becomes part of your toolbox, which I think is awesome. So, for example, then I also changed some opaque constructions or made some of my own. Here they are. Um, I also, we won't go over this now, but I created some custom schedules for natural ventilation. And I did that just by following a tutorial that they did, which was very helpful. Okay, but let's just go look now then at my first template here. You know what I'm going to do? I'm going to actually stop, and so that this doesn't get just too long. And I'll have another video that's talking about the runs.